hopefully you've already met these concepts during your first year. So variability, accuracy and precision. So it's important that you understand that there's natural variability between experimental units, participants, however you want to call them, the people, the things that are inside your experiment, or between even test tubes. That experiments can actually introduce extra variability. When you use your pipette, you're adding a bit more variability depending on how you use it. Then there's a difference between accuracy and precision, and you need to understand the concepts of bias and variation, and think how pairing can help to reduce between individual variation. So there can be a massive amount of natural variability between experimental subjects. You can just look at the variations in heights, weights, metabolisms, responses to diet of humans. We're all an individual and all different. So the problem with a biological experiment is if the difference between individuals is larger than the difference between treated and untreated, between treated and control, then you won't be able to see any effect of your treatment. Now, the variability of an experiment is usually measured by the standard deviation or the variance. Now, where does this variation come from? Now, some of it can be systematic because you didn't design your experiment very well. You've introduced some more variation. So that can depend on the equipment you use for your experiment. For example, I was working as a chemist, and when you do a quantitative titration in chemistry, you use volumetric flasks and you make sure that you measure things on balances that have the grams to 5 decimal places, and they're placed on rigid benches so there's no effect of vibration, and there's all sorts of things you can do to improve the reliability of your experimental equipment and make sure that when you say something is 1 molar, it is exactly 1 molar or as close as you can get it. Whereas if you put in a beaker, you're approximate to within maybe 5%. So experimental design weaknesses introduce some variation. Another thing is chance or random variation. That can depend on the day of the week and the bad luck of the particular person. And then there's unforeseen effects, things that you couldn't have anticipated. So an example of this was a very sensitive physics experiment in the University of Cambridge in the Cavendish laboratory, and they were doing the experiment and they couldn't figure out why the experiment only worked on Tuesdays. But on Tuesdays, a large van, so collecting the bins, went past the laboratory, and it was the movement of that van that was causing the experiment to behave differently on Tuesdays to the other days of the week. If you have something unexpected in your experiment, you need to check it first before running out and saying, I've just discovered something amazing, because often it turns out just to be a mistake. Now, hopefully you've seen this sort of slide before. So looking at bias and variation, accuracy and precision, because you did this during your first year biochemistry experiment. So in diagram A, you've got low bias but high variation, so low precision. So you're getting the right answer, which should be in the bullseye in the purple region, but you've got quite a lot of scatter around. So you've got low precision, low replication, precision. When you repeat the experiment, you're getting quite a lot of variation introduced from either the experimental units or the way you're doing it. B, the points are much closer together, so you've got a higher level of precision, but you're biased. You're nowhere near the accurate and correct result, which should be in the middle of the bullseye. C is the worst possible case. You've got lots of scatter, so you've got low precision, and you've also got bias, so you're nowhere near the accurate and correct result. And D is exactly where you want to be. All of your points are very close together, so you've got high precision and you're accurate. you've got low bias, and you're in the center of the bullseye. Now you can actually deal with the case of B. So that means you've got high precision, but you're not in the right place. So that's called a systematic error. Now, if you can identify the systematic error by some kind of calibration, then you can move all your data to the correct place. Now, one thing that you might have used in the first year was the coefficient of variation. So the standard deviation has the same units as the mean of that particular measurement. So if you divide one by the other, the two sets of units cancel out from each other and they make what's called a dimensionless quantity. So it's a dimensionless quantity that measures the variability of your data and its precision. So it tells you how many standard deviations of variability you have. Now this is good when you're trying to compare the variability of two data sets which are on very different scales. So for example, I want to know what's the variability and weight of an elephant and the variability of weight in a mouse. Now if I did that in kilograms or grams, that's very silly because they're on completely different scales. The variability between two elephants is going to be many times even the total weight of your mouse. So what you're doing is saying, what's the variability in terms of numbers of standard deviations? Now, one way of removing subject variation is this idea of pairing. What you can do is measure the effect of an individual but without treatment, and then so that's their control measure, and then measure what's happened when they are treated. So for a blood pressure drug, I measure the blood pressure before, measure the blood pressure afterwards. Now this is pairing. So you have a pair of measurements from each of the experimental subjects. So these two measurements are not independent of each other. So you can always tell when I've got a data set which is paired within SPSS because I end up with two columns for the same making of the same measurement. Now, paired versus unpaired design. So in a paired design, we take samples from each patient before and after and look at the difference. In an unpaired design, you have two groups of patients, one that you treat and the other is untreated. Now, which of these two makes a better experiment? Now, most of the time, it's going to be the paired experiment. But still, you have an effect because when you've got paired data, your number of data points is halved because they're not independent of each other. The before and after, those two come as one pair rather than two individual data points. So that means if you've got a limited budget for collecting data, you end up with a much smaller experiment if you're doing paired.